Alright, hello everybody and welcome to a new problem from the arrays chapter. This problem will show us how powerful and simple it is to sort an array when needed and how it will change the whole problem and become very smooth to solve, right? So, this problem is called Arithmetic Progression Array and we are going to read the statement together. We are given an array of integers and we should check if all its distinct values can be rearranged in such a way that they form an arithmetic progression. And if so, we should return its ratio, right? Every arithmetic progression has a ratio, and we are going to see the definition of that in more detail a little bit later. Otherwise, if there is no way to rearrange only the distinct values in such a way that it forms an arithmetic progression, we will just return 0, right? Because as we have at least two distinct elements, there is no arithmetic progression to have the ratio 0 because, it consists of only one distinct value. So, let's take a look at the example first. And let's see. I have an array which consists of 11 integers, but as you can see, some of the integers are equal, right? So for example, I have a 40 here and I have two more 40s here. So as you can see in the problem, it says that we need only its distinct values. So first of all, let's take a look at this array, but only consisting of distinct values. So what I'm going to do here is pretty simple. I'm going to iterate for each and every value, and I'm going to see if that value has already been pushed into the new array, right? So 180, no. 30 is the next one. 80 is the next one. 280 is the next one. 130 has already been pushed, so I do nothing here. 330, 230, I already have 30. I already have 340 and I already have 80, right? So this is my array that consists only of the distinct values. Now, I have to rearrange these values in such a way that I can obtain an arithmetic progression. So let's see first, what is an arithmetic progression, right? Well, an arithmetic progression is a series or a list of numbers which follow the following formula. So the first one will always be the first one, right? So let's denote the arithmetic progression by A. The first element is always A of 0. It could be positive, it could be negative, doesn't really matter. The second element will be, of course, some A0 plus some integer. Whether if this element is greater or smaller than A0, there definitely exists some integer such that the second element could be written like this. Now, the thing is that the difference between these two, which we noted here by R, is called our ratio, right? Is the ratio of the arithmetic progression. Then, if we know the ratio, which is R, each and every next element will be written as the previous one plus that ratio, right? So I can write the third element as A0 plus 2 times R. I can write the next one as A0 plus 3 times R, right? So basically, as you can see, the difference between each two consecutive elements is the same, and is this ratio, right? And of course, so on and so forth until I have the last element, which again will be written as something as A0 plus some number K crossed R, right? So this is how an arithmetic progression of length, how much? Well, this is 0 times R, 1 times R, 2 times R, and so on and so forth, K times R. So this is this is an arithmetic progression of length K plus 1. And this is how it looks like, right? Now, as I said, this ratio could be either positive or negative, doesn't really matter. It can even be 0 if our arithmetic progression consists of only one element. Otherwise, it shouldn't be. So, first of all, let's take a simpler scenario, and let's suppose that in this array we have only distinct values. So we don't need to filter only the distinct ones and make another array. Let's suppose we already have them, like here, right? Now, if we have this array, look how it should look like in the end, right? So, it has a first element, and then each and every next element is increased by R. I have the first case scenario, right? In which R is greater than 0. If R is greater than 0, think about it. I have A0, then I have A0 plus R, right? Which is A1. So A0 plus R. And this R is positive, which means that A0 will be strictly less than A1. Perfect. Then I have A0 plus 2 times R. What does it mean? R is positive, so this one is definitely strictly less than the next one. So A1 is strictly less than A2. And so on and so forth. A2 will be less than A3, and so on and so forth, until the last element, which let's say is A0 plus K times R, right? And again, everything will be less than the last element, which is A of K. Awesome. So if R is strictly positive, is greater than 0, what we can see here is that our arithmetic progression is definitely going to be strictly increasing, right? Now, following the same line of reasoning, of course, if I choose an R which is strictly less than 0, so a negative R, what's going to happen? Guess what? A0 is the first element. Then I have A0 plus R, because R is negative, of course. This is going to basically, A0 is going to get decreased, right? When we get A1. So it's strictly greater than A1, which is strictly greater than A2, and so on and so forth, until everything is strictly greater than AK. So what you can see here is that if R is negative, this arithmetic progression is actually strictly decreasing. This is very important because the problem asks us to see if the values can be rearranged. And what we did now is that from the, let's say, k factorial ways of rearranging some k values, right? There are k factorial ways, basically each and every permutation of that list of integers. From all of those k factorials, we have just reduced them to only 2 possible options. The first one is having them sorted increasingly, and the second one is having them sorted decreasingly. But let me tell you one thing. We can actually reduce it to only one of them. We don't need to check both. And you know why is that? Let's just suppose that this is a valid thing, right? So if I take all these integers and rearrange them in strictly decreasing order, I get an arithmetic progression, right? Let's suppose this is true. If this is true, this means that I will have a correspondent arithmetic progression with the ratio that is positive. And let's take the example to see what I mean by that. In this example, where I have all these distinct integers from here, let's see what happens when we sort them in increasing order. Which is the greater one? The greatest is 330. Awesome. Next one. It should be 280. Awesome. Next one. It should be 230. Awesome. Next one. It should be 180. Next one. It should be 80 and then 30, I guess, right? So how many elements do I have? I had 6, now I have only 6. Perfect. So what is the ratio here? If the first element is 330, it gets decreased by 50, so the ratio is minus 50, right? This one is this one plus minus 50. Also, what happens here? Wow, still minus 50. Perfect. What happens here? Still minus 50. Awesome. What happens here? Well, I don't like what happens here, actually. It's not minus 50. And why is that? That is because I have, of course, forgot to write the 130 here. So you might have noticed this. I'm sorry about it. No problem. Let's also add the 130, right? So yeah, I forgot to add it when taking the distinct values here. Alright, so now actually this example became valid, right? It's going to be 130, 80, and then it's going to be 30. Awesome. So now here we have minus 50. Now here we have minus 50. And here we also have minus 50, right? So what's the thing here? The thing is that having them decreasingly sorted, I find that they form together an arithmetic progression with the ratio equal to minus 50. Awesome. Now think about this. If in decreasing order, they always get decreased by minus 50, right? First element, minus 50, minus 50, minus 50. What happens if I really reverse this order? So, of course, I take the elements in the increasing order. Now, the first one will be 30. The second one will be 80. If their difference, 30 minus 80 was minus 50, now their difference, the second one minus the first one, will be 50. So I take 30 first, I take 80 the next one, and see what happens. Their difference is 50. Third one is 130. Look what happens. Their difference is 50, right? Because it's supposed to, because if the second minus the first is, of course, R, then the first minus the second will be minus R, right? Then the next one will be 180. Wow, still a difference of 50, and so on and so forth, right? So, one observation, which I find pretty cool, right? It's not like mandatory to make the observation in order to solve the problem. You could have tried out, let's take the elements in increasing order and see if they form an arithmetic progression, and let's also take them in decreasing order and see if they form an arithmetic progression. But why do that when you can tell the interviewer, look, it's exactly one thing. Trust me, they love this. They love when you can come up with such smart observations that basically get us rid of an entire portion of the code or doing the same thing when it's not necessary, right? Awesome. So in the end, in this order, I'm going to have an arithmetic progression of ratio 50. So what's our conclusion here? Our conclusion is that if we have an array which consists only of distinct values, then all we need to do is rearrange those values in increasing order and check if they form an arithmetic progression. And how do we check that? Well, it's actually really simple, right? How did we check it here? We have written the elements in the respective order, and we have seen for each two consecutive elements what's their difference. And this is it. Their difference should be always equal, right? So the difference of the first two, which is supposed to be the ratio, should be equal to the difference of the next two and the difference of the next two, and so on and so forth, right? This is all we need to do. After sorting the elements increasingly, we just compare each difference of two consecutive elements, and they should be in fact all equal. If they are, we have ourselves an arithmetic progression and we can return that ratio. Awesome. Now, remember that we have supposed that we will have an array only full of distinct values. Now, what we have to do is actually solve the problem when we don't have only distinct values. Well, we already know how to do that, don't we? Because we have solved the problem remove duplicates. In that problem, we had to do the same thing, and our approach was sorting the array and then traversing the array and storing only the distinct values in place. You can go and rewind that lesson if you don't remember how to do it, but we're not going to do it here, of course. So using the approach from remove duplicates, we are going to have our initial array nums transformed into an array which consists only of distinct values, and even more than that, those distinct values are going to be sorted increasingly. Because if you remember, we first sorted the array and then kept only the distinct values. This is perfect. We basically got what we need. All we have to do afterwards is traverse the array and check if all the differences of two consecutive values are equal. And if so, we return that difference, right? Because it's 1, and otherwise we return 0, and that's it. Let's see how the code looks like, and then analyze the time complexity of the approach. Alright, and here is our algorithm. So, first of all, I'm going to apply the function remove duplicates, right, from that problem. Make sure you go check that code out if you don't know how to do it anymore. And of course, as I said, the time complexity for this one is going to be big O of n log n, right? Where n is the number of elements the nums array has initially. And then what I'm going to do is have this difference of the first two elements, nums of 1 minus nums of 0, stored in one variable r. This is constant, of course. have the new length of the nums array after removing the duplicates also noted by m. And then what I'm going to do is compute the differences of each and every other pair of consecutive elements, right? So we start from 2 and we go all the way to the last one, n minus 1, and check if nums of I minus nums of I minus 1 is different than r, then we know for sure this is not an arithmetic progression, right? So we return 0. And of course, after finishing this for loop, if we end up here, this means that all those differences are equal. They are all equal to r. So I'm just going to return this value. Now, what is the time complexity of this? As I said, this is constant. This is constant. We have a for loop which performs how many? N minus 2 iterations, right? Because we start from 2 and go all the way to n minus 1. And we have just an if statement and a return in the worst case. So yeah, this code is linear, right? So we have big O of n from here, and the bottleneck is of course the first state, which is big O of n log n. So we have come up with a solution to this problem in big O of n log n. And now of course I have a follow-up for you. This is big O of n log n, and also important to mention, it is big O of 1 in terms of memory complexity, right? Because remember, removing the duplicates takes place in place, right? Removing the duplicates is performed in place. We don't use any extra arrays or stuff like that, and we don't use any extra data structures or arrays here. So it is big O of n log n time and big O of 1 memory complexity. Now, of course, I have a follow-up problem for you. Can you solve this problem in linear time, so big O of n, knowing one thing? You know that in the initial array nums, right, that we receive in the input, each and every element from there, each and every element nums of I is going to be less than or equal to 1000, right? So we are given very small elements, and let's also suppose that they are greater than or equal to 0. That doesn't matter. So each and every element in the input is small. It is at most 1000. Knowing this, can you come up with a solution that is going to be big O of n in terms of time and not actually constant, but also smaller than big O of n in terms of memory, right? So yeah, you probably guessed that it's going to be something to do with this 1000, but I'm not going to give you any more hints. Enjoy the coding for this problem and think about the follow-up.